All right, so we're going to pick up here where we left off on class on Friday, talking about the second law of thermodynamics. So remember, the second law of thermodynamics deals with entropy. Entropy of the universe increases for spontaneous processes. And we talked that entropy is just a measure of the motion of the particles. So the more motion we have in our particles, the more energy we have, and the more entropy we have. So looking at entropy, you can also think of it as chaos or disorder. And so the more motion we have, the more chaos we have, the more disorder we have. And so for spontaneous processes, the entropy of the universe will go up. It's a positive value. And remember, we talked that spontaneous processes are processes that occur without any outside intervention. And so remember, spontaneous processes, it doesn't matter how fast or how slow they occur, just that they occur without any outside intervention. And we talked about rusting, metal rusting. That's a relatively slow process, but it's a spontaneous process. We talked about ice melting. That at room temperature is a spontaneous process. It doesn't happen instantly, but it might happen faster than a nail rusting. And then a combustion reaction, when we looked at the whoosh bottle or the methane bubbles, that was instantaneous. And so once we mixed those chemicals together that we needed, the methane gas with the O2 and ignited it, that was spontaneous, and that was instant. So spontaneous deals with occurs without any outside intervention, not dealing with the speed. We'll look at speed of reactions, how fast or how slow they are later on. And so we can look here and we can look at it like a formula, if you will. So looking here, let's start down here at this one. Delta S of the universe. So we know that change is just final minus initial. Or here, when we're looking at change, we're looking at system versus surroundings. And so we're looking at the entropy of the system and the surroundings, and that would give us the overall entropy of the universe. And so for a spontaneous process, we would say delta S is positive, greater than zero, right? Spontaneous processes increase the entropy of the universe. And so we know that then you can write down spontaneous processes are irreversible processes. And so comparing that to reversible, remember we talked Friday, reversible processes are processes that we can do the exact opposite of what we did and get back to the exact same state or the exact same thing we started with. And you can go back and look in the notes previously dealing with this piston and lifting the partition and dropping the partition when you try to wrap your mind around reversible versus irreversible processes. So know that spontaneous processes are irreversible, and so irreversible processes that change in entropy of the universe is greater than zero. And so we know that all spontaneous processes will increase the entropy of the universe. And so when we look at spontaneity or whether a process is spontaneous or not, we can look at entropy is one thing we can look at. And if entropy is a positive value, that means it's spontaneous. If entropy is a negative value, delta S is negative, that means not spontaneous. And so we talked Friday as well with ice melting. Temperature plays a big role in whether ice melting, whether it's spontaneous or not. At room temperature, there's enough energy in the environment around us for it to be spontaneous, right? You put the ice on the table, it melts. Nothing else you had to do. However, if you put ice in the freezer, there's not enough energy in the freezer to melt it. So temperature plays a role. That melting of ice becomes not spontaneous. And so those are two of the three factors that affect spontaneity, temperature and entropy. And so entropy, here we see entropy of the universe will increase for a spontaneous process. And we can later, we'll look at practice questions where we look at different situations and try to see whether they're spontaneous or not. One thing we can look at is, does delta S, is it a positive or negative value? If delta S is positive, it's spontaneous. If it's negative, it's not spontaneous. And when we look at entropy, we mentioned entropy is motion. So the more motion we have, the more entropy we have. And we looked at on Friday talking about if you're just sitting in a room, there's not a lot of motion, so there's not a lot of entropy. But if you all were to get up and walk around the room, there's more motion, so there's more entropy. If you were to get up and run around the room, that would be even more motion, even more entropy. And you can relate that to the motion of our molecules. The more our molecules are moving, the more entropy they have. And so temperature is one way that we can measure the motion of the molecules. And we look at average kinetic energy, right? Kinetic energy is the energy of motion. And so as temperature goes up, kinetic energy goes up, and that means our molecules are moving more. They're moving faster. And so temperature, remember, temperature and heat are two different things. So temperature is just a measure of the motion, measure of the kinetic energy. Now, the more motion there is, the more kinetic energy they have, the more they'll collide and brush past each other, creating more friction, which then creates heat. And so that's why things that are hot have a high temperature, and it goes back to having more motion. And so we can look at three types of motion: translational, vibrational, and rotational motion. The more of these that we have, the more entropy we have. And so translational is pretty easy to understand. You take a molecule and it moves from point A to point B, so it's moving around. Those are our gas molecules, right? Gas molecules are moving around from point A to point B. Solids aren't doing that. Like wherever you're at, if you're sitting at a table, whatever the solids around you, they're not moving from point A to point B, so they don't have translational motion. Vibrational motion, you can look at the diagram there. When we can see here the molecules, the bonds there, they're just vibrating, so moving in and out, in and out. This one's moving back and forth, and then here they're both moving out and in, so that you could think of the molecules vibrating. And then rotational motion, we just have a sigma bond. Remember, sigma bonds are just single bonds. So if we have a double or triple bond, we don't have the rotational motion. But when we have a single bond, you can have the rotational motion. And so here you see the molecule is rotating. And so the more types of this motion we have, the more entropy we have. And so gases have the most motion, right? They have all three types, whereas solids, they don't have all three types. So solids only have vibrational motion. And then you can look at liquids. Liquids probably have vibrational and some rotational, and then gases have all three. And so we can look at entropy on the molecular scale when looking at the different types of motion that are present. And so we look at microstates. We can look at just taking a snapshot of the molecules, and the different snapshots that we would get shows a microstate. The more microstates we have, the more entropy we have. Don't worry too much about these microstates. You won't be asked to calculate them. You'll see a formula on the next slide. We're going to skip it. We don't need it. But the only thing you need to understand is the more motion our molecules have, the more entropy is present. And so solids to liquids to gases are gaining, the temperature's going up. They're gaining heat, which they're gaining kinetic energy. And because they're gaining kinetic energy, they're moving more. And so the entropy is increasing. So don't get hung up on microstates. Don't get hung up on this formula. We're not going to solve it. Just understand that as W, which is the number of microstates, which really is just how much motion do we have. As W goes up, S goes up. So as the motion goes up, the entropy goes up. That's all we're looking at here. And so the number of microstates and therefore entropy, again, really we're just looking at motion. So don't let microstates confuse you. We're just looking at the motion. It increases with an increase in temperature, volume, and particles. And so why would temperature increase the entropy? Well, as you increase the temperature, what are you doing? You're speeding up the molecules. As you speed the molecules up, they're moving more. As you have more motion, you therefore have more entropy. Increases in volume. So why would increases in volume cause an increase in entropy? Well, if you increase the volume, you can think of this a couple different ways. I mean, how would you increase the volume of a liquid? You add more liquid. If you increase the volume of a gas, you add more gas. So that will relate to this point, but if you spread them out, the molecules have more space to move, more movement, more motion, more entropy. And then here, if you can just think of this as the molecules. If you take 10 molecules versus 100 molecules, right? 100 molecules, there'll be more motion. More motion is more entropy. So just understand entropy is related to motion, and then if you understand the behaviors of the molecules, then you can understand how entropy is increasing under certain conditions. And so we talked here Gases have the most entropy. Remember, S is our symbol for entropy. Gases have the most entropy. Solids have the least amount of entropy. Again, more motion, more entropy. And then, so we look at solutions again. So remember, solution is just dissolving something in a solvent. And for us, most of the time, the solvent is water. In general, when we dissolve something, the entropy is going to go up. And so why is the entropy going to go up? Well, what happens when you put something into water? Let's say NaCl, right? NaCl goes from one particle, right? Na and Cl bonded together, and then it's breaking apart into two ions, Na plus and Cl minus. So you can think of it as I'm starting with one particle, NaCl, as the solid molecule bonded together, and then I put it into water and it's breaking into two different things. Because you're going from one thing to two separate ions, so NaCl to Na plus and Cl minus, because you're going from 1 to 2, you have two particles instead of one. Two particles is more motion, and so the entropy would increase. And this is in general. It's not 100% all the time, so we'll say in general. So don't get hung up on the exceptions to this. For AP, for this class, for the exam, they want you to know when you dissolve something in a solvent, and again, us, mainly water, the entropy is going to go up. And so you can look at these different scenarios of entropy increasing. So when gases are formed from liquids and solids, so entropy increases. If I start with solids and liquids and I end with gases, entropy went up, right? Solids and liquids have less energy, gases have more energy, so more motion. And so liquids or solids or solutions are formed from solids. So again, if we start with a lower entropy state and end with a higher entropy state, entropy has gone up. If you look at the number of gas molecules increasing, and so that means entropy would go up as well. If on the left side I have 3 gas molecules, the right side I have 5 gas molecules, right? Then that means we have more molecules, we have more motion. And then number of moles, this is similar number of gas molecules here. We can look at this process here. You can look at the number of moles or the number of gas molecules. There's 2 here and 1 here. That's 3 on the left. 2 here, that's 2 on the right. I went from 3 here to 2 here, so this is an example of entropy decreasing. You went from 3 gas molecules, or you went from 3 moles on the left to 2 on the right. So because 3 down to 2, that means entropy decreased. We'll stop there for today. Make sure that you look at the practice questions based off what we've just talked about. If you need to go watch this video again, please do so. And remember that I'll have my office hours later this afternoon if you can't answer the practice questions. So we'll see you there.